Hello friends, let's begin the lecture number 12 of Advanced Thermodynamics. In the previous class we were looking at the mathematical statements of the second law of thermodynamics, and towards the end we were also looking at how to use the Carnot cycle to define the measurement method for thermodynamic temperature. And because the thermodynamic temperature cannot be practically measured using a Carnot cycle, because Carnot cycle, which is a reversible cycle, is not practically feasible, we were looking at an alternative method of using the ideal gas temperature scale for measuring the absolute temperature. We also said that there can be an infinite number of absolute temperature scales so long as all of them have the same origin. The origin is at condition when the energy of the object goes to zero, but the size of the graduation can be chosen from infinitely large number of values, and for each of those it gives you a different thermodynamic scale. So each student in the class can create a thermodynamic scale on his or her own name and do that, and all of them will be equivalent. They'll only be different from each other by a constant ratio factor, okay, which is the ratio of the size of the graduation. That's just like your Celsius and Fahrenheit temperature scale, where the distance or the temperature difference between the boiling point and freezing point of water at atmospheric pressure is divided into 100 units in Celsius and 180 units in Fahrenheit, and they give rise to the Kelvin scale and the Rankine scale, which have a ratio of 1.8 between them. So 1.8 graduations of the Rankine scale is equal to 1 unit of the Kelvin scale. So that's the basic difference. Otherwise the origins are common, and you have possibility of absolute scales which are infinite. Now in this class we'll take the mathematical statements that we defined in the class a little bit more forward and see how the Corollaries statement, which gave rise to the mathematical statement of second law in the way that we derived in the last class, leads to the various already known corollaries or statements of the second law of thermodynamics from your undergraduate classes. So for that, let's go to the whiteboard and we will start from there. So if I take the Cauchy's inequality, which states the second law for a cycle, this basically tells you that the cyclic integral of del Q by T is less than or equal to 0. The less than applies when the cycle is irreversible, and the equal to applies when it is reversible. So to apply to any general power cycle, what is a power cycle? A power cycle is one where there is a high temperature reservoir and there is a low temperature reservoir, and there is an engine which operates between the two and produces power output. It takes in QH from the high temperature reservoir, gives QC to the low temperature reservoir, and produces work equal to QH minus QC. Okay, this is the first law for the cycle, which is the net work is equal to the heat in minus heat out. Now if I apply the Cauchy's inequality to a power cycle, we would get QH TH, which is positive because QH is coming into the object. So if I take this as the object, the engine, then QH comes into the object, so it is positive. So QH by TH, and if the magnitude of QC is taken, then it is going out, so minus QC by TC is less than or equal to 0. This is your expression for a power cycle. So we can rearrange this to say QH by TH is less than or equal to QC by TC. Okay, or the other way around, we can take the temperature to one side and heat flux to the other side. Then you will get QC by QH is greater than or equal to TC by TH. And if I write the in terms of the efficiencies, then in terms of efficiencies, it is 1 minus QC by QH, which is the efficiency of the actual cycle, because QH and QC are actually happening there. And 1 minus TC by TH is the efficiency of a Carnot cycle. So if I write this, because of the negative sign, the inequality will get reversed. So 1 minus QC by QH is less than or equal to 1 minus TC by TH. This is the expression that you get from here, which basically says that the thermal efficiency of any real cycle is less than or equal to the thermal efficiency of the Carnot cycle. So the highest efficiency that can be achieved in a power cycle is the Carnot efficiency. This is our classical Carnot theorem. It says that the thermal efficiency of any cycle is less than or equal to eta Carnot. So when the cycle is completely reversible, its efficiency approaches or it attains the Carnot cycle efficiency. But if it is even slightly irreversible, even any one of the processes is slightly irreversible, its efficiency goes down below the Carnot efficiency. So that is your Carnot theorem. So this is one of the concepts that we had studied from the undergraduate thermodynamics, and we can actually obtain it from the mathematical statement of thermodynamics, second law of thermodynamics, which we derived from the Corollaries statement. So in one way, it establishes the equivalence of the Corollaries formulation with the classical formulation that we have studied earlier. Taking the same expression further, we said QC by QH is going to be greater than or equal to TC by TH, right? So if I write the expression for QC, this gives QC is greater than or equal to QH into TC by TH. Okay, so this is the expression that you get. Now we know that this TH can never be equal to 0, because we had looked at it from the basic definition of absolute temperature. T is del E by del S, as other variables are kept constant. Now this would go to 0 only when the E approaches 0, and it approaches 0 faster than S. So the absolute zero temperature can at most be approached, but can never be attained. So C, therefore, is a positive quantity. It will never be 0 or negative. Similarly, TH is going to be a positive quantity. So TC by TH is a positive quantity, and QH we have defined it to be positive. So the right hand side is greater than or equal to 0. Okay, so this is something that we know. In fact, it is never equal to 0, it's always greater than 0, because temperature can never attain equal to 0. So this will be equal to 0 only when TC goes to 0. So it will be greater than 0. It basically says there should be QH, which is non-zero in any power cycle. This is basically the statement of Kelvin Planck, which says that you cannot produce work continuously by exchanging heat only with one reservoir. That is, there needs to be a rejection of heat So the efficiency of any power cycle can never be 1. It has to be less than 1. So QC greater than or equal to 0 is nothing but the Kelvin-Planck statement of second law. So we had studied Kelvin-Planck statement of the second law for power cycle, saying that whenever there is a heat engine cycle, it always needs to interact with two reservoirs. You cannot produce work taking heat from only one reservoir, which basically means that you have to reject heat to a second reservoir if I take energy from the first reservoir. So QC greater than or equal to 0 basically is the same as the Kelvin-Planck statement. Okay. So this is again another method of showing equivalence of the calculatory formulation with the decimal formulation. The same concept or the same Clausius inequality, if I apply it to a refrigeration cycle or a heat pump cycle, then it is, let's say, Tc and Th, where Th is greater than Tc. Okay. Then the refrigeration cycle is a reverse cycle which takes in energy from the low temperature reservoir and delivers energy to a high temperature reservoir, and this work in is equal to QH minus QC. So we are defining all positive quantities here. Wn is a positive quantity, QH is a positive quantity, QC is a positive quantity. So QC goes from the low temperature reservoir and QH goes to the high temperature reservoir, and this is the work input. So now if I apply the Clausius inequality to this situation, then I get cyclic integral of del Q by T is less than or equal to 0. Here QC is a positive quantity because it comes into the system, and QH is a quantity with a negative sign, so because it goes out of the system. So I can write QC by Tc minus QH by Th is less than or equal to 0. That is your finding from the Clausius inequality. So if I rearrange this, then it basically tells me QH is greater than or equal to Th times QC by Tc. And now I know that by definition, for a heat pump cycle or a refrigeration cycle, the Th is higher than Tc, and therefore this Th by Tc is always greater than 1. So this basically means this is greater than 1, and therefore QH is always greater than QC. Okay. So this is your definition that you will get. So for any real cycle, this QH has to be greater than QC, and which basically also goes to mean, and since Tc can never be equal to 0, this equality sign will also not come into place. It will be just greater than QC, which basically means that Wn is greater than 0. So this is the Clausius statement, which basically says that I cannot run a heat pump cycle without any work input. I will need to produce or give some work input in order to be able to pump energy from a low temperature reservoir to a high temperature reservoir using a cyclic process. So this is the second statement of second law of thermodynamics that we have been used to, and we have shown that this is also equivalent to the statement of Clausius inequality, which we derived from the calculatory formulation. So by this we can actually say or summarize using the PowerPoint slide that I will just show you, that the Clausius inequality applied to a power cycle gives you this expression, from which we can say 1 minus QC by QH is less than or equal to 1 minus TC by TH, which is the Carnot theorem. And from the same statement, we can say QC is greater than QH into TC by TH, and since TC can never be 0, the right hand side is positive, then it tells you QC is greater than QH, which is a QC is greater than 0, which is the Kelvin-Planck statement. And the Clausius inequality, when it's applied to a refrigeration or a heat pump cycle, this gets reversed. So you get QC minus TC, QC by TC minus QH by TH is less than 0. And this basically, since QH is greater than TC, you get QH is greater than QC, which basically means there should be a work input. And that is the Clausius statement. Now let us look at how to calculate entropy change in the case of an irreversible process. So we'll move to the whiteboard. So we know that for a reversible process, ds is equal to delta Q by T. So this is something that we are already aware of, because we derived this expression from the second law, saying that delta Q in a reversible process is theta ds or Tds. Okay, but so if if the process is reversible, the ds is basically the integral. So delta s is going to be the integral of delta Q by T. But for an irreversible process, we know that ds is greater than or equal to. So in the case of irreversible process, it will be greater than delta Q divided by T. Okay. So because this is an inequality, it's not clear how to determine this. Or if I write it in the form of an equation, then it becomes ds is equal to delta Q by T plus delta sigma. So in order to evaluate the change in entropy, we also need to know how much is the entropy generation, which we do not know. But one thing that we are also aware is that in any process between an initial state, let's say, and a final state, let us say this is I, this is F, if I have an irreversible path, okay, the same two states can also be connected through a reversible path. Okay, so if I want to calculate the entropy change from I to F, which is SF minus SI, that can be then the integral of delta Q by T along the reversible path, and that will also be the same as the entropy change between the other two states, because entropy change is only for state function, it only depends on I and F and not the path. So that is the factor that we take advantage of in evaluating the entropy change for an irreversible process. So let us say, okay, so SF minus SI is equal to the integral of delta Q by T through the reversible path. Okay, so this is basically from I to F through the reversible path. So this is basically what we take advantage of. So whenever we need to calculate the entropy change for an irreversible process, we construct a reversible path between the same two states and calculate the entropy change for the reversible path, and that gives you the entropy change for the irreversible process as well. So let us work it out by two examples. One is the example of short circuiting of a battery. All of us know that short circuiting of a battery is an irreversible process. Let us try to plot that on the EQE diagram. So on the EQE diagram, this line represents the constant S, or the reversible adiabatic line, and if this is our state I, and the battery is short circuited but it does not undergo any heat transfer, let us say the heat transfer is not there, it's an adiabatic process. So an irreversible adiabatic process of short circuiting will actually bring the charge down from here to here through this irreversible path, which is a dotted line. Let me draw the irreversible path in a different color. Okay, so let me erase this and show the irreversible path in different color. So it will be red. Okay, so this is the irreversible path from I to F. Now the same process, if I try to calculate the entropy change by constructing a reversible path between these two. So what I try to do is to drop an ordinate from here to here. So let us say this is QEI and this is QEF. So between the same QEI and QEF, suppose I go through a process which is reversible adiabatic. So I discharge the battery using an external voltage which is only infinitesimally lower than the internal voltage of the battery at all times during the discharge process. Okay, and once we get to charge QEF, then we stop the discharging process. Now we see that the energy at this level, which is EI equal to EF, is the energy at this location, EF prime, if I call this point as F prime, which is a reversible adiabatic process from I, then EF prime is lower than EI because the electrical energy has been now spent. Now, in order to get it back to state F from F prime, the Q needs to remain the same. So the charge is not changed. So there is no charging, discharging that is done. But you basically supply heat through a reversible process in the sense that now, because the battery has not been short circuited, it's not hot. It is actually at room temperature, let us say, and it has been reversibly adiabatically discharged. So now, in order to get the battery to the temperature at which it would have reached, if the battery were adiabatically short circuited, you need to add heat, and the heat would be equal to the EI minus EF prime. That much of energy has to be added through a reversible heat transfer process. So in order to calculate then SF minus SI, which is the entropy change for the irreversible process, we calculate it through the process of SI to SF prime and SF, so I to F prime and F prime to F. So it will be SF prime minus SI, this is the first process, plus SF minus SF prime. Okay, so this is the two processes, and now we know that F prime and I have the same entropy, and therefore this will be 0, and SF minus SF prime can be evaluated for a reversible heat addition process as SF minus SF prime is equal to integral from F prime to F of delta Q by T. And if this process, because if I write the first law for the process from F prime to F, since there is no charging or discharging happening, the work is 0 because QEF is constant, and therefore there is only heat addition that's happening. So EI or EF minus EF prime is equal to the delta Q integral of delta Q. This Q and QE you need to differentiate. This Q is the heat transfer from F prime to F, right? So since this is known, actually instead of writing the integrated expression, we can actually write the first law in the differential form for the path. It will actually be dE. So delta Q is actually equal to dE for this process. Okay, so this will be equal to integral of dE by T from F prime to F. Okay, so if E is given as some heat capacity C multiplied by T, then dE will be C dt. So if I can do that, then I can integrate this as C outside dt by T from F prime to F, and that gives you the change in entropy. This is equal to this, so that will be the change in entropy for the irreversible process. Exactly in the same fashion, we can also evaluate the change in entropy for process, an irreversible process of expansion of a cylinder piston, let us say. So let us take that example here. So free expansion of gas in a cylinder piston. Okay. Now this free expansion is process of expansion against vacuum. So suppose I had a cylinder piston here with the piston initially at this location and is locked, and here there is vacuum, and here there is, let us say, Pi, the initial pressure. And if I remove this pin and I have, let us say, stops here, so it does not expand to infinity, but it expands up to the stops. So then this, let us say, is Vi, and when the piston finally goes and stops here, let's say the total volume is Vf. Okay. So then if I draw the E versus volume line here, here we know that the reversible adiabatic line goes like this, and let us say the initial state is somewhere here. So correspondingly this is Vi, and suddenly it expands. So, and so if the sudden expansion is happening adiabatically, let us say, then the final state will reach an Vf, okay, with the same energy. Okay, so if I show the irreversible process in a different color, then we get this. Here is this line, and show that with a dotted line in red. Okay, so then the say if this is state I, this is state F, this will be state F prime. Okay, then we can replace the IF by a state IF prime and F prime F exactly in the same way as we did there, and this would be a reversible adiabatic expansion where the external pressure is only infinitesimally lower than internal pressure at all points in time during the expansion here. And once we reach Vf, we lock the piston like we have stopped here, and because now the gas has done work on an external pressure, so its energy would have decreased, and so it would have come to Ef prime, and now we'll need to take it to Ef by supplying heat in a reversible fashion such that the temperature difference across which the heat is supplied is infinitesimal at all points in time. So then the entropy change for this process is 0, and the entropy change for this process is delta Q by T, and this delta Q is equal to delta E, and if delta E for the gas is the mass into specific heat into T. So if I dE is mc dt, so if I take out the mc and integrate dt by T, I get log Tf by Tf prime, and that multiplied by mc will give me the Sf prime minus Fi, Sf, which is also equal to Sf minus Si. So exactly in the same fashion as the previous case, this can also be evaluated. So in order to evaluate the entropy change for an irreversible process, we basically need to construct a reversible path between the same two states, initial and final states, and then calculate the change in entropy for the reversible path, because that will be the same as the entropy change for the irreversible process. So we'll pause at this point and continue in the next lecture. I think we have done the first and second laws in their corollaries at this point. From the next class onwards, we'll be looking at equations of state for simple compressible systems to start with, because they are the most familiar ones, and then generalize the equations of state for other systems also. We did mention about equations of state in one of the previous lectures. We'll carry on with that concept, where the equation of state is basically a relationship between the generalized force, generalized coordinate, and temperature. And if there are multiple modes of interaction possible, generalized forces, generalized coordinates, and the temperature. So there will be one equation of state for each mode of interaction, and they will be connected through temperature. So this is basically what we'll be starting to do from the next class onwards. We'll stop here for this class. Thank you.